Hi, my name is Nick. My talk today is titled SwiftSyntax for Good and Evil. Oh, I'm sorry, that's a typo. It should be SwiftSyntax for Good and Eval. So what is SwiftSyntax? So the SwiftSyntax GitHub page describes it as a set of Swift libraries for parsing, inspecting, generating, and transforming Swift code. Why a set of libraries? Well, SwiftSyntax isn't just one library. The SwiftSyntax package actually contains 16 separate modules. That's not including tests and internal helpers. I won't attempt to cover them all, but these are the ones we'll be looking at today. So how does SwiftSyntax actually work? Well, at the core of SwiftSyntax is a data structure called the syntax tree. The tree consists of nodes, each representing parts of a Swift program. The root of the syntax tree is the source file. From the root grows branches that represent statements, expressions, declarations, and so on. The leaves of the tree are tokens. Those are indivisible source code elements such as keywords, identifiers, and literals that have no children of their own. Now, you might have heard of an abstract syntax tree, an AST. This is a concrete syntax tree, a CST. In an abstract syntax tree, only the actual statements, expressions, and so on are stored. In a concrete syntax tree, everything from the original source code is preserved, including comments and whitespace and so on. All nodes in the Swift syntax tree conform to syntax protocol. Every distinct element has its own struct type. Tokens are represented by token syntax. Function declarations are represented by function decl syntax. Why do they write out function in full but write decl for declaration? Your guess is as good as mine. And so on, all the way down to source file syntax. Okay, but what is Swift syntax useful for? Well, Swift syntax is already used for several things within the Swift compiler itself, evaluating conditional compilation directives and Swift macros, of course. And it's also used within Xcode for the Swift migrator, refactoring tools, fix-its for errors and warnings, and for code formatting. And beyond that, there's many other useful applications, linting, static analysis, code generation, and so on. But there's many great tools for all of these things already. So what if we try something a little bit different? Most scripting languages have some form of eval function. JavaScript, Ruby, Python, PHP all have this concept. Eval is a function that takes a string of source code and runs it. Languages that support runtime code evaluation make it easy to write apps that are scriptable, can be extended with plugins to customize their behavior, or support new workflows. Now, Swift is my favorite language, and so I've often wished there was an eval function for Swift. But Swift is a compiled language, and the Swift compiler is a very complex, monolithic piece of software. It's not a dependency that you can easily include in a Mac or iOS app, especially not in the App Store. But now that we have SwiftSyntax to take care of the parsing side, all we need to do is the actual evaluation part, and how hard could that be? Well, let's find out. We'll start with a simple mathematical expression, no functions, variables, or loops, just numbers and operators. Before we can evaluate the expression, we need to parse it. So let's import the Swift parser module. Next, we'll call parser.parse to generate the Swift syntax tree, and then we'll use debug print to print it out. And the result is what we see on the right here. Now, there's a lot going on here, but for now, let's focus on the sequence expression syntax node. Sequence expression syntax is how expressions are represented in Swift syntax. Basically, it's a flat list of operators and operands. And here we have our first hurdle. It's a problem I like to call operator soup. As Sophie expertly explained to us on Wednesday, mathematical expressions can't just be evaluated from left to right. Some operators have higher precedence than others. Multiplication takes precedence over addition, for example, so it has to be evaluated first. But in Swift, operators are defined in the language itself, so programs can define new operators. And you can even redefine built-in operators and alter their precedence or associativity. And because of this, Swift syntax can't know the precedence of a given operator at parsing time. It might not even know what a given operator is at all until it's parsed the declaration for it, and that could be in a different file or even in a different module. So Swift syntax doesn't attempt to resolve operator precedence at parsing time. It just produces this flat expression list. And the thing is, we can't directly evaluate an expression in this form. We'll need to figure out the precedences, and then we'll need to extract the expression into a new data structure that we can traverse in the correct order. Fortunately, we don't actually need to do that because Apple already did it for us. SwiftSyntax has a module called Swift Operators that's specifically designed to solve this problem. We'll start by importing the Swift Operators module. The operator table type keeps track of known operators and their precedences. Swift operators can populate the operator table by parsing source code and finding operator declarations in that code. But operator table actually has convenient standard operators default instance, and that comes primed with all the built-in operators from the Swift standard library, and that's sufficient for our purposes. Finally, we need to call operator table fold all on the syntax tree, and we'll get this result shown on the right here. If we compare this with the original tree on the left, you can see that the sequence expression has been collapsed into these nested infix operator nodes, and this represents the correct order of operations. Okay, so with that solved, I think we're ready to write an interpreter. So unlike a compiler, which turns source code into executable code, an interpreter is a program that just executes the source code directly. The main interface for our interpreter is this evaluate function. And what this will do is it'll take a source tree, such as the one on the right, and it'll evaluate it before returning the result. And to do that, we'll need to write a function that recursively visits each node in the tree and then dispatches to other functions to perform the appropriate logic. But we don't actually have to do that because Apple already did it for us. So syntax visitor is a utility class that traverses a syntax tree, and it optionally calls user-defined functions for each node that it encounters. The main entry point for syntax visitor is this walk function, and this accepts a syntax node. And syntax visitor is actually an open base class, and it's got stub implementations for every type of node that it can visit. So to provide our own functionality, we just need to subclass it and then override the visit functions for the syntax types that we're interested in. So to implement the interpreter, we'll first import the SwiftSyntax module, and then we'll set the superclass of interpreter to syntax visitor. And then in our evaluate function, we'll call the inherited walk function to do the actual traversal. And to actually perform the evaluation, we need to override a couple of the visit functions from syntax visitor. We'll start with the integer literal expression syntax visit function. This will just parse the integer literal value and store it in result. And then slightly more complex, we need to add a visit function for infix operator expression syntax. And what this will do is it will recursively call our evaluate function for the left and the right operands, and then store those results in local variables. And then we'll switch on the operator token and apply appropriate logic. Okay, so that's the basic implementation for the interpreter done. To test it, we're going to create a program called a REPL, which is a read, eval, print loop. Here's the code for it. So the REPL's main loop reads an expression that's input by the user. We parse and fold the source tree, evaluate the result, and then print it back to the console. Let's see it in action. Okay, we'll start with something simple. You can't get much more simple than that. And it works, success. We'll try an expression with multiple terms. Okay, good. So the order of operations is working correctly. Division, that also works. Divide by 0, that's also fine, working with doubles. Let's try a fractional value. Okay, it's not what I expected. And what if we make a deliberate syntax error? Okay, so I kind of expected some sort of parsing error. What about an unknown operator, plus plus? Okay, looks like we crashed. Okay, so to figure out what's happened, let's take another look at our interpreter code. So the first bug was with fractional input values. And here's the problem. We added a visit function for integer literals, but we don't have one for float literals. That's why it just returned the default nan value from the evaluate function. So that's easily fixed. We'll just add a visit function for float literal expression syntax as well. Next, we've got the deliberate syntax error. So I wasn't expecting this to produce a meaningful result, but why didn't we get some sort of a parsing error for this? If we examine the REPL code again, so here's where we parse the input. And parser.parse doesn't throw or appear to return any errors at all. So how does SwiftSyntax handle invalid input? Well, there's several reasons why a source file might include unexpected syntax. It could be a programmer error, but it could also just be new syntax that this version of the parser isn't aware of yet. And even if it is a typo, we expect a modern compiler to report all the issues it encounters in a single pass, not just bail out after the first error. So instead of discarding unrecognized input, SwiftSyntax preserves and encapsulates it so that it can continue to work with the rest of the code. Unexpected node syntax is used when the parser finds some code that it doesn't understand. And there's also a family of syntax nodes related to missing code from the input. And these act as placeholders for gaps in the source tree so that the parser can continue to construct the rest of the tree without being blocked. And finally, for even more granularity, every token has a presence property, indicating whether it was actually found in the input or whether it was inserted by the parser to fill a gap. It's great that SwiftSyntax is able to recover from errors, but working with broken input can be dangerous and lead to more serious errors later on. So how can we detect and report these errors instead of just ignoring them? Well, Syntax Visitor can traverse these missing or unexpected nodes just like any other kind of syntax node. We glossed over it before, but the Syntax Visitor initializer has a view mode parameter that controls how invalid syntax should be handled. And you can choose between source accurate, fixed up, or all as the modes for that. We're currently using fixed up for the interpreter, but if we switch to all, we could add visit functions for the missing or malformed syntax nodes, and then we could produce a list of errors. But we don't actually need to do that because Apple already did it for us. So the parser diagnostics generator class provides a simple way to get a list of errors and warnings from a syntax tree. To use it, we first need to import the Swift parser diagnostics module. Then to get the parsing errors, we'll run parser diagnostics generator diagnostics4 on the syntax tree. This returns an array of diagnostics, which we can just print out. And finally, we'll bail out if there's any errors, rather than continuing with the bad input. So let's see how the output looks now. OK, good. That's a lot more helpful than nan. Note that the error even includes the line number and character position. So what about that crash when we use the custom operator? Is that also fixed now that we're logging the syntax errors and bailing out rather than proceeding? No. So if we actually look at the crash message, it seems like an error is being thrown at the top level of the app. And there's also a pretty strong clue here that the error relates to the Swift operators library. So if we take another look at the REPL code, the operator table fold all call is actually the only line that's marked with try here. So it's the only line that could be throwing an error. The question is, why is it throwing? We initialize the operator table with all of the operators from the standard library, but ++ isn't a standard operator in Swift. Now, the Swift syntax parser is happy to ignore undefined operators. But operator table can't fold an expression if it doesn't know what the operator is. So instead of failing silently, it throws an error. The operator table fold all method accepts an optional error handler callback. The default behavior is to throw, but we can actually provide our own implementation to handle the error more gracefully. The callback's parameter is an operator error. What we actually want is a diagnostic here, but operator error has a asDiagnostic method that we can use to convert them. So if we replace the throwing fold all call with one that appends the operator errors to the existing diagnostics array, let's try our REPL again. So there's our error. OK, so that's much better. And let's try some more expressions. 4 + -5. OK, well, that's not right. So by now, you can probably guess what's happened. We never added a visitor function for prefix operators. So the unary minus here is just being ignored. But this time, it's not even returning nan to indicate that something went wrong, because it doesn't know that something went wrong. So it's just silently skipping the negation step and giving us the wrong result here. What we really need is a reliable way for the interpreter to detect when it encounters some syntax that it doesn't support yet. Now, overriding every single visit function exposed by the syntax visitor just to log a diagnostic doesn't sound like much fun. There's like almost 300 of these methods. But fortunately, we don't actually need to do that because Apple already did it for us. So syntax any visitor is a subclass of syntax visitor that adds a visit any fallback method. And visit any is called for any syntax type that we haven't added a more specific visit function for. It comes at a slight cost of performance. So if we modify the interpreter to inherit from syntax any visitor now, we don't need to touch any of our existing visit functions, they're fine. And we'll just add a new override for visit any. Now, ideally, we'd like to log some kind of an error here, but for now, we'll just return nan so that we can actually verify that it works. If we try the problematic expression again, okay, good. So it's hitting our fallback and not just failing silently anymore. Call me suspicious, though, but yeah, okay, it looks like we actually broke everything. So the problem with using nan to signal errors is that it doesn't really give us much debug info to work with. Can we make use of SwiftSyntax diagnostics here somehow? Maybe we can raise our own diagnostic errors. Let's find out. So the diagnostic type is just a struct, which is defined in the Swift diagnostics module. The initializer has a bunch of parameters, but the only ones we need to think about are node, which are the syntax node that spawned the diagnostic, and message, which is a type conforming to the diagnostic message protocol. The diagnostic message protocol is an extension point for creating our own diagnostic messages. Now, SwiftSyntax doesn't provide a concrete diagnostic message type for general use, so we'll need to define our own. We'll start by importing the Swift diagnostics module, not to be confused with the Swift parser diagnostics module, which is what we used earlier. We'll define a message struct that conforms to diagnostic message. And note that this doesn't have to be a struct. It could be an enum if we wanted to define like a fixed set of errors. And to save some typing, we'll also add this convenience method to syntax protocol, just to make it easier to throw diagnostics. And finally, we'll add the diagnostics property to the interpreter, and we'll replace that nan result in visit any with a diagnostic call instead. We'll also need to update the REPL logic again. So first, we'll move the evaluation up to before we print the diagnostics. And then we'll append the interpreter diagnostics to the array and clear them so that we don't accumulate errors between iterations. Let's see if that helps us get a better sense of what was going wrong with the evaluation. Okay, so here's our expression again. Okay, so that's quite a lot of info, and it's rather more errors than I was expecting. But we can see in the middle there that we have the unhandled prefix operator expression, which we figured was the issue. If we try a simple expression again, okay, so that's why it wasn't working. But what are all of these unhandled syntax nodes that we're seeing here? So if you recall the syntax tree from earlier, the Swift syntax parser always returns a source file syntax node. Even for a single line expression, that gets packaged as a statement inside a code block inside a source file, and it's terminated by an end of file token. So previously, we were ignoring these container nodes by just overriding the visit functions, by not overriding the visit functions for them, and that was fine. But now anything that we haven't explicitly overridden is going to raise a diagnostic in visit all. So to solve that, we now need to explicitly ignore those by adding no-op visit functions for all of those container types. And now, with any luck, yes, okay, so now only the problematic syntax is being flagged. And if we try our simple expression again, it's back to working. Okay, but what about something like this? Okay, that's a lot of errors. Or this, maybe? Okay, so it seems like we're still a long way away from having a fully fledged Swift interpreter here. It's time to upgrade our expression evaluator. So we're going to support strings and Boolean values. In order to do that, we're going to introduce an enum type called variant. And this is going to replace double values in our interpreter. We'll also add a dictionary property to store the named variables. And then we need a visit function for decal reference expression syntax. That's a reference to previously declared identifiers, such as function types or variables. And we need a visit for variable decal syntax as well, which is the syntax for declaring variables. Okay, so we're making progress, but what about functions, loops, conditional statements, and so on? All of these things can be implemented using the techniques that we've already covered, but since we're short on time, I'm going to skip ahead. If you're interested in the implementation details, you can check out the example links at the end. Okay, so let's take stock. If we try some variables, now an expression. Okay, so that all seems right. How about a deliberate type error? Okay, good. An unknown variable. Okay, perfect. All right, so we've seen a lot of trivial test examples. Now let's try some real code. This is a Fibonacci function. It returns the nth element in a Fibonacci sequence. This uses recursion, conditional statements, comparison operators. I'm sorry that it's all in one line, but we don't currently support multi-line statements. So let's try this with a couple of values. Okay. Nice. But something's bothering me. You see the int parameter and return types in the Fibonacci function declaration here. So we've specified that these are integers, but we don't actually check them at all. In fact, we can define a function like this with completely made-up types, and it makes no difference at all. Our interpreter doesn't have any concept of types, only values. And it seems wrong to allow type annotations if we're just going to ignore them. So what if we rejected them instead? We already reject other valid Swift syntax that we don't support yet, so let's just do the same for types. Now, you might think that we could add a visitor function for type annotations to the interpreter, but that won't actually work. If it did, then the visitAny function would already be catching them. The reason it doesn't work is that the type annotations are child nodes of their respective variable or function declarations. And those visit functions are returning skip children because they already contain all of the logic needed to process those nodes. So the visitor never actually traverses the type annotations at all. So what we need to do instead is create a separate syntax visitor that operates as a pre-processing step prior to running the interpreter. This preprocessor follows exactly the same pattern as parser diagnostics generator. So it has a diagnostics for function that creates an instance and invokes the walk method to generate the diagnostics. And then we've got visit functions for variable type annotations, function return types, and function parameters. And the parameters case is a little more complex because the type signature in a function parameter is not actually a syntax node in its own right. The type is part of the parameter node. And so we still need to preserve the other things, such as the parameter name. So instead of rejecting the entire parameter node, we'll inspect its properties to see if it has an explicit type. And the easiest way is just to check for the presence of a colon. So next we'll need to update the REPL so that it calls the preprocessor and captures its diagnostics. And now let's test it. So if we try and use an explicit type now, we should get an error. And we do. Let's try it with a function. Okay, great, it's working. Now let's try a variable declaration without a type. Okay, that works fine. And finally, let's try our Fibonacci function again, but this time without parameter or return type. Okay. All right, so I see what's happening. It's not the preprocessor that's raising this error, it's actually Swift parser diagnostics. So the real Swift parser doesn't allow function parameters that don't have types. So parser diagnostics generator is raising this error. But our preprocessor now won't accept functions that do have types. So how can we satisfy them both? Well, what if we modify the preprocessor to actually insert the missing types before we run the regular Swift parser diagnostics generator? So syntax visitor isn't able to modify the syntax tree while it's traversing it. And for that, we'll need to use another Swift syntax utility class called syntax rewriter. So if we change the base class of our preprocessor from syntax visitor to syntax rewriter, and then next we need to update the visit functions. Syntax rewriter follows a very similar pattern to syntax visitor, but unlike syntax any visitor, it's not actually a subclass of it. And the visit method signatures are very slightly different. Instead of syntax visitor continue kind, each one of these visit functions returns a copy of its input node instead. In most cases, we don't actually need to modify those at all, because the variable and function return types are optional anyway in regular Swift, so it's fine to just omit them. But function parameters must have types to be valid syntax. So we'll need to update the visit function for function parameter syntax to repair these typeless parameters that we're now mandating in our preprocessor. So first, I'll mark the colon as being present so that parser diagnostics generator won't complain that it was missing. Then I'm going to insert a parameter type. So the type itself doesn't matter. We just need to put something there to make the syntax valid. I've used any here, but I could have put foobar. And finally, I'll replace the diagnostics for entry point with this new process method. And what this will do is it'll accept the source file syntax as an in-out parameter so that it can modify it as well as returning the diagnostics. And note that syntax rewriter doesn't have a walk method here. We just call visit directly. Because we've changed the API for the preprocessor, we also need to make a small adjustment to the REPL code. The source syntax now needs to be mutable, and we'll pass it by reference. And that's all done. So we should now be free to write Swift unencumbered by types. Let's try our Fibonacci function again. Success, there's no warnings. Let's try another function. This is a square function. That works fine. OK, I got a bit excited and mistyped the name here, but at least this proves that the error checking is working. But wait a second. Undefined is not a function? It seems very familiar. Where have I heard this before? OK, something has gone very wrong. So I set out to make an eval function for Swift, but this isn't Swift. Swift is strongly typed. Swift has static safety checks. And Swift is fast, and this is none of those things. It might be SwiftSyntax, but what I've created here is JavaScript. So maybe that evil wasn't a typo after all. OK, so we're over time, so I'll have to leave it there. I can only apologize for this terrible crime against Swift. If you're interested in learning more about this, you can find the source code for everything that I've shown today here on my GitHub page. Thank you.